Continuing on with lesson 9, talking about gases. So in this lesson, we are going to actually start by talking about Dalton's law of partial pressures. We'll relate that to mole fractions and do some calculations with that. Understanding kinetic molecular theory. This will lead us into rate of effusions with Graham's law and doing those calculations. We'll also learn how to distinguish real gas from an ideal gas. In this lesson, we'll be introduced to a few new vocabulary terms. We'll talk about vapor pressure, discuss mole fractions, the difference between diffusion and effusion, and relate that to Graham's law of effusion, and then also about van der Waals forces. So you can see there are some new equations off to the right that we will learn how to use as well. We're going to start by looking at the first equation on that list, which is utilizing the ideal gas law. If you remember from the last video, the ideal gas law was PV is equal to nRT. So you'll notice in this equation, they are replacing the V part with MW, molecular weight. And then on the other side of the equal sign, we have dRT. So instead of nRT. So we have molecular weight and density being our two differing variables within this equation. So let's look at what those variables mean and what units we will need them in when using the equation. So P is still pressure in ATM, just like it was in the ideal gas law. MW stands for molecular weight. When we're using molecular weight, it is in grams per mole. We can calculate the molecular weight of any element or compound by using the periodic table, as long as we have the chemical formula. The D in the equation is for density of a gas. Now notice the units. Okay, so we've always looked at density so far in this course in either grams per milliliter or grams per centimeter cubed. The units for this equation are grams per liter. So not milliliter, but liter. So keep that in mind. Now that R value, that's that gas constant we discussed before. So that is given to you, and it will always be 0.08206 liters ATMs per kilogram, or Kelvin mole, excuse me. And then T stands for temperature, and then of course the temperature needs to be in Kelvin when we're using this equation. So let's try using that equation with an example problem. So in this example problem, it's asking what is the temperature of gaseous NO2, nitrogen dioxide. It gives us the molecular weight of nitrogen dioxide. However, if it didn't, we could calculate it based off of the chemical formula using the periodic table. The gas density that they're giving us is 3.26 grams per liter. Notice it's in the units we want, so we won't have to change that at all. And then the pressure they're giving us is 1620 millimeters of mercury. Now that is not the units we want. We want ATM, hence the conversion factor in parentheses after. So let's write down a list of what we know. So we know the molecular weight of nitrogen dioxide, the density in the correct units, the pressure, which remember we're going to have to convert into ATM. We have the conversion factor, of course, and then one piece not given to us in the problem itself, but that we know because it's the gas constant, is that R value. So we're going to be using the equation PMW is equal to dRT. First, we're going to convert our pressure into ATM, and then we'll rearrange the equation to solve for temperature, that variable T, and solve. So converting the pressure in ATM first, we start with the pressure they gave us in millimeters of mercury, 1620, putting the 760 millimeters of mercury in the denominator so that the millimeters of mercury can cancel, leaving us with units of ATM. So Dividing those two numbers, 1620 divided by 760, we get 2.13 atmospheres. Next, we need to rearrange the equation now that we have all of our variables in the correct units. So we take the original equation, move both the R and the D onto the other side of the equal sign by dividing both sides by dr. That will leave T by itself, coming up with this rearranged equation off to the left, or excuse me, the right. Now we can plug in the numbers. So we have 2.13 for the atmospheres, multiply that by the molecular weight of 46.01, divided by that R value, the gas constant, multiplied by the density. So we get 366 Kelvin. Now, since it didn't say specifically to put it in degrees Celsius, you can leave it in Kelvin. However, if you did want to convert it, the converted into Celsius would be 93.2. So let's try another one utilizing the same equation, except for this time it's asking us to solve for molecular weight. Feel free to pause and try this one on your own. So, like I said, we're calculating molecular weight. They're giving us a temperature. Notice the units. It's in degrees Celsius, so that will need to be converted to Kelvin. The pressure they're giving us is 0.888 atm. That's good. Correct units. Nothing to change there. Density given to us, grams per liter. Now, one thing they didn't give it to us is that R value, that gas constant. Okay, but since we know what equation we're going to use, we can just fill that in when we write our list of knowns and unknowns. So molecular weight's got the question mark by it because that's what we're solving for. Units are going to be in grams per mole. For the temperature, like I said, we need to convert. So whenever we're converting Celsius to Kelvin, we add 273.15 to it. So we get a new value of 350.35 Kelvin. Pressure stays the same. Density we didn't need to change or convert, I should say. And then, of course, there's that R value, gas constant. So we take our original equation and rearrange it so that we have molecular weight all by its lonesome on one side of the equation. We do that by dividing both sides by pressure, so that pressure is in the denominator now. On the other side of the equation, once we have that, we can plug in our knowns. So plugging in our knowns, our density multiplied by that gas constant multiplied by the temperature in Kelvin, and dividing all of that by 0.888 atm. We get a value for the molecular weight of this compound at 167 grams per mole. Moving on to the next topic, we're going to discuss Dalton's law of partial pressures. So notice so far when we've been talking about gases, we've been talking about one gas in particular. For example, one of the last problems we did had nitrogen dioxide gas is what we were focusing on. Well, what if you have more than one gas present, a mixture of gases? Well, that's where Dalton's law of partial pressure is going to come in. So this P sub T stands for total pressure. So the total pressure is going to equal the sum of its parts. So the pressure of gas A, pressure of gas B, pressure of gas C, so on and so forth for however many gases are present. The total pressure is going to equal the sum of its parts. So when we're doing that, when we talk about air composition, for example, here's a breakdown of the air composition, an example. So notice the air is made up of mostly nitrogen at 78.08%. That's the one shaded in green here. Then we have oxygen being the next highest, present in 20.95%. And then, of course, a whole bunch of other trace elements present. So if the pressure at sea level, for instance, is 1 atm, meaning the total pressure, 1 atm, that means that that total pressure of 1 atm is equal to the sum of all the gases that are in the air at sea level. So if we were using this, for example, with the air composition pie chart off to the left, that entire pie chart is equal to 100%. right? So each of those parts added together equal the 100%. Same thing goes if we change that to 1 atm. So instead of 100%, all those gases combined equal 1 atm. So that means 0.7808 atmospheres make up the nitrogen contribution. 0.2095, that's that 20.95%, we just changed it to a decimal. ATM are oxygen, and then the next highest one, that 0.93% of argon, we change from a percent to a decimal, getting 0.0093 ATM of argon. Notice those other trace elements that were very, very tiny amounts are not included in the overall total pressure. Now, usually, when we are figuring out partial pressures, we are not going to be using this equation. Okay, this equation is just to see the concept that the total pressure is equal to all of its parts, the sum of all of its parts. Okay, when we're trying to figure out the partial pressure of a specific gas, we're going to use the ideal gas law. PV is equal to nRT. And you'll see how to do that in just a moment here. All right, so here's an example of when you would have to calculate partial pressure. So if you have a mixture of gases and you wanted to know the partial pressure of just one of those gases, okay? So in this particular question, we are asking for the partial pressure of carbon dioxide in a gas mixture that contains 4 grams of nitrogen gas, 4 grams of carbon dioxide gas, 4 grams of chlorine gas, and all of those gases are present in a 6-liter container, and that container has a temperature of 298.15. Okay, so let's break this down into what we know. Well, I said before on the previous slide that to figure out the partial pressure of each gas, the equation we're actually going to use, you can see at the bottom of the slide here, is PV is equal to nRT. So let's see how we're going to use that. First off, if we write down all of our knowns, so we're using that equation, we know we're going to need volume. So I'm writing volume, 6 liters, it's in the units we want. Temperature, they also gave us. They gave it to us in Kelvin, also the units we want. Now, here's the tricky part. Pressure is what we're going to solve for, because that's what it's asking for, the partial pressure of carbon dioxide. We have the R value, but what piece are we missing? Well, we're missing the N in that equation. So if you remember what the N stands for in that equation, it stands for moles. They didn't give us the molar amount of the gases present. Instead, what they gave us were the masses of the gases present. So I know that the mass of the carbon dioxide is 4 grams. I can figure out how many moles that is by dividing that gram amount by the molecular weight of carbon dioxide. So I would need to figure out the molecular weight of carbon dioxide. I do that by using the periodic table, getting a total mass of 44.009 grams per mole. So what do we want to do next? Well, let's figure out that N value. Let's figure out how many moles are present. So if I want the moles of just carbon dioxide gas, I take the mass, 4 grams, divided by molecular weight, 44.009. Doing that, I get a value of 0.0909 moles. Okay, so I have all the pieces of information that I need, and I can solve now for pressure. So let's see how that's going to look. So this equation that we're using, PV is equal to nRT, we only need to solve for the partial pressure of the carbon dioxide because it's not asking for the partial pressure of the chlorine or of the nitrogen. Those were extra pieces of information. So to solve for the partial pressure of just carbon dioxide, I rearrange the equation to get this guy here, putting volume in the denominator. Next, I plug in my values. So I want to make sure I'm plugging in the moles of just the carbon dioxide because I'm looking for the partial pressure of just the carbon dioxide. So that's the key part there. If I wanted to figure out the partial pressure of chlorine, I would do the same exact thing I'm doing now. I would just use the moles of chlorine that were used. So I would have to solve for that. So the mole part is representing the carbon dioxide. You multiply that by the gas constant, R. Multiply that by the temperature they gave us, 298.15, because that's the temperature of the carbon dioxide in the mixture as well. And then as far as the volume goes, we want the volume of the entire container that it's in. So 6 liters, that's the volume given to us. That's the volume of the container that the carbon dioxide is in. So solving for all of that, getting it down to 2 significant figures, the answer for the partial pressure of the carbon dioxide is 0.37 atm. Let's try another practice problem using partial pressures. So remember, when we're solving for partial pressures of a mixture, we're going to be using that PV is equal to nRT. So we're just changing the pressure for partial pressure of whatever gas we're solving for, and the N value will be the molar amount for whatever gas we are solving for. So let's look at the problem. So the gas we're solving for, they're asking for, is the partial pressure of sulfur dioxide. Okay, so that's what we're going to focus on, is just the information pertaining to sulfur dioxide. So notice they give us the mole amount of H2, hydrogen gas. That's also a gas present in the mixture. We're probably not going to need to use that since they're not asking about hydrogen gas. The next piece of information, they're giving us the moles of sulfur dioxide. We'll definitely need that, right? That's going to be our N value in the PV is equal to nRT, because that's our moles, our N of SO2. Now they're also giving us moles of helium, another gas in the mixture. We won't need to use that because we're solving for partial pressure of sulfur dioxide. Now they give us the volume of the container, so the 2 liters, that's our V. And then they give us a temperature, 27 degrees Celsius. Now notice it's in Celsius, so we are going to have to convert that into Kelvin. So what we know the volume, 2 liters, no conversions needed there. Temperature, 27 degrees Celsius. We add 273.15 to convert it into Kelvin. Next, we need our N value, moles. Moles of what? Well, moles of sulfur dioxide, because we're solving for the partial pressure of sulfur dioxide. So the moles of sulfur dioxide was 0.040. Notice we did not need the moles of helium or hydrogen gas in this case. That R value, it's part of the PV is equal to nRT equation, so we're going to need that gas constant to use in solving. So to determine the partial pressure of sulfur dioxide, like I said, we're using PV is equal to nRT. We need to solve in this case for P, for the partial pressure. So we do that by removing V to the other side of the equation. That goes into the denominator. So we have our rearranged equation here. Once we have rearranged our equation, we can plug in our knowns, solving for our unknowns. So we have our molar amount of just the sulfur dioxide, 0.040, multiplied by our gas constant, and our temperature in Kelvin, divided by the volume of the container to get a total partial pressure for sulfur dioxide gas of 0.49 atm. Now we are going to combine the ideal gas law, the PV is equal to nRT, along with stoichiometry. So if you remember stoichiometry, you need a balanced chemical equation. It is when you are taking an amount of one reactant and converting it to an amount of a different reactant or product. So that's why we need the balanced chemical equation for it. So there's going to be multiple steps in this problem, and we'll just work through it step by step. So let's look at the problem to start off. What are we solving for? Well, first question is asking for volume. So that's going to be the V of our PV is equal to nRT. Volume of what? Ammonium chloride gas. So that means we're looking for the volume of this guy here in the equation. That's the ammonium chloride, NH4Cl. Notice they use the term STP. So the fact that they use the term STP, which means standard temperature and pressure, that's my clue that I'm using PV is equal to nRT. Because that's the only time they'll talk about standard temperature and pressure is when we're using the ideal gas law. So it gave us a temperature then of 273.15 Kelvin and a pressure of 1 atm. So that's what the STP, they gave us two variables just by saying STP. So we're solving for volume. We have temperature and pressure so far. So let's keep going. So can be produced by the reduction of, so they're giving us an amount of 10 grams, but notice 10 grams of what? Nitrogen gas. So let me highlight this in a different color. So that 10 grams, that amount is pertaining to nitrogen gas, not to the ammonium chloride. Okay, so they're saying you have 10 grams of this reactant. What is the volume of ammonium chloride product that you will get out of it? It is asking us then, after we solve for volume, to calculate percent yield, given that 12.4 liters was actually produced experimentally. So we'll save that percent yield for last. Let's dive into the first part. So writing down what we know, it's always a good place to start. So remember STP gives us a temperature of 273 and a pressure of 1 atm, so that's two of the variables we need. Now notice they give us a mass of N2. I also wrote down the molecular weight of N2 because that's something you can solve using the periodic table. We are going to need that. Why are we going to need that? Because if you can look at our roadmap over here, we're going to have to go from grams of N2 to moles of N2 because we need it in moles in order to compare it to anything else in the balanced chemical equation. So once we have moles of our nitrogen gas, we can then use a mole ratio to convert that to moles of the ammonium chloride gas. Okay, so that's what we're going to need the molecular weight for. Now, we also wrote down an R value. That's the gas constant that we're going to be using in the PV is equal to nRT equation that we have right here. And then also notice we have a ratio here. So let's just write this quickly. So the molecular weight we're going to be using in this first step, going between grams and moles of nitrogen gas. So we will divide by the molecular weight to go between grams and moles. We will then use the mole ratio. I'm just going to write MR for mole ratio. In the second step here to go from moles of N2 to moles of NH4Cl. So notice the mole ratio given is 1 to 2. How did they get those values? Well, it is looking at the coefficients in front of nitrogen gas and in front of ammonium chloride. So if you look at in front of nitrogen gas here, there is no coefficient, so we assume it's 1. So that's saying 1 mole of nitrogen gas will produce 2 moles of ammonium chloride gas. So that's how we get this 1 to 2 ratio, and we'll be using that in this second step here to convert between moles of N2 to moles of ammonium chloride. Once we have the moles of ammonium chloride, that will be our N value that we can plug into the PV is equal to nRT equation so that we can solve for the volume it is requesting us to solve for. So lots of steps in this problem. All right, so our plan is to start with the gram amount of N2, so that 10 grams they gave us in the problem. We are going to be using the molecular weight of nitrogen gas to convert from grams to moles. Once we have moles of nitrogen gas, we are then going to use that mole ratio, the 1 to 2 mole ratio we talked about on the previous slide, to get it into moles of ammonium chloride. Once we have moles of ammonium chloride, we have our last variable needed in the PV equals nRT equation so that we can solve for volume in the end. All right, so let's start our plan. So we're going to start with our grams of nitrogen gas. So it was 10 grams. We then divide by molecular weight in this case, putting the molecular weight 28.014 gram portion on the bottom so that grams and grams cancels. So if we stopped at this step, we now have moles of N2. But we need to keep going to use the mole ratio. So remember, it was the 2-to-1 mole ratio. We're putting the 1 mole on the bottom because that's representing the nitrogen gas. That way, moles of nitrogen gas and moles of nitrogen gas are on opposite sides of that horizontal line and they cancel. The 2 moles of ammonium chloride on top. So solving, we get a molar amount of 0.714 moles of NH4Cl. So this is going to be our N value that goes in the PV nRT equation. Our next steps then, now that we have all the variables needed, is to solve for the volume, because that was the original question, right? Solve for the volume of ammonium chloride gas. We had to use stoichiometry so that we could figure out the moles of the ammonium chloride gas produced so that we had that N value for this equation. Now that we have that N value, we have everything we need to solve for volume. So let's rearrange the equation to solve for volume. So to do that, we need to put pressure on the other side of the equal sign. So we divide both sides by pressure. That gives us a new equation with pressure in the denominator and volume all by itself on one side of the equal sign. We then put in our knowns and unknowns and solve. So our molar amount that we calculated based off of stoichiometry was 0.714 moles of ammonium chloride. We multiply that by our R value, the gas constant, 0.0206. Multiply that by the temperature in Kelvin. Since the temperature was standard temperature and pressure, that's where we got the 273 from, standard temperature, STP conditions. And then in the denominator here, we have 1 atm because standard pressure is 1 atm. So calculating all of that out, we get a total volume for ammonium chloride gas produced to be 16 liters. Now that is the theoretical volume. So why am I pointing out that's the theoretical volume? Because notice the next question. The next question is asking us to calculate percent yield. So percent yield, we take our actual amount produced and we divide it by the theoretical amount produced and multiply that by 100 to get the percent yield. So this amount here, this 16 liters, this is the theoretical amount. So let's look how we're going to solve for percent yield. So like I said a moment ago, percent yield, we take actual amount produced, which is going to be this 12.4 liters, that's the amount you produced during the experiment, divided by theoretical, which we solved for on the previous slide, which was 16 liters. Multiply that by 100 to get it into a percent. So we put 12.4 in the numerator, being the actual or experimental. 16 goes in the denominator. Notice the liters are canceling, and that's why the units on it are just percent. So divide 12.4 divided by 16 multiplied by 100, and we get a total percent yield of 77.5%. Next, we're going to discuss mole fractions, and we're going to be relating that to partial pressures. So this X of A, that is the mole fraction of gas A, as you can see. Now, how do we figure out the mole fraction of gas A? Well, you would take the molar amount of gas A and you would divide it by the total moles. So we represented this with variables by writing N sub A divided by N sub T. So N sub A being moles of A, N sub T being total moles, because we've always used the lowercase n as a representative for moles in a lot of our equations. Now this can be related to partial pressure according to the following equation. So partial pressure of gas A divided by the total pressure of the gases in the container. So those would be equal to each other. So looking at an example of this. So the total pressure, when we're solving for that, we take the partial pressures of all the gases present. So the sum of all the partial pressures equals the total pressures. It's the same thing for the total mole amount. The partial moles of all the gases in the container, the sum of all of those partial amounts equals the total amount of moles. So let's do some examples and relate mole fractions to partial pressures. So for example, if we wanted a mole fraction of N2 in the container off to the right, well, looking at the container off to the right, nitrogen gas is represented by the orange spheres. So looking among them, I see there is one orange sphere. So that means there is 1 mole of nitrogen gas, and there's a total of 10 moles in the container. I know that by adding all the spheres in the container. So that gives me a mole fraction of 1/10, or 0.1 if you want it in a decimal amount. Now, if I were to change that to the partial pressure of N2, it's going to be the same. So that's why we can set them equal to each other. Same thing goes if I tried it for any of the other gases present. So I'm going to go over these ones a little quicker. For hydrogen gas, for instance, hydrogen gas being the red spheres. Hydrogen gas, there are 3 moles of hydrogen gas present out of the 10 in the container. That gives me a fraction of 3/10, and that would be the same fraction if I was figuring out the partial pressure of hydrogen gas. Same goes for oxygen, being the yellow spheres. There's 4 out of the 10, giving us 2/5. Carbon dioxide, last but not least, there are 2 moles of carbon dioxide present. That's 1/5 of the amount, meaning same partial pressure. So what we're trying to point out here is that we can set these equal to each other, the partial mole amount and the partial pressure amount, because we are essentially solving for the same thing when it comes to the container and all the gases mixtures present. So we're going to utilize this equation that we just derived in the following examples. So in this practice example, we have a mixture containing 8.50 grams of methane gas, or carbon tetrahydride, giving us a molecular weight. In parentheses right after that, we also have hydrogen gas, it looks like, 8.5 grams of hydrogen gas present. Notice they're also giving us the molecular weight of hydrogen gas. Now those two gases combined exert a pressure of 1.32 atm. Now using this equation that we just derived, that Na over Nt is equal to Pa over Pt, we need to calculate the partial pressure of each gas. So that means we're going to have to use this equation twice. We will use it once where A is the methane gas, meaning this sub A here, and then we'll use it again where N sub A and P sub A are representing the hydrogen gas moles in pressure. So let's look. We're going to start with the partial pressure of CH4 because I said we have to use that equation twice. So I've changed the A now to CH4 so that we know exactly what we're dealing with. Now, in order to use this equation, we are going to need to figure out the total amount of moles. They did not give us the total amount of moles. What did they give us? They gave us the total pressure, so this 1.32 atm, that is our P sub T, so that they gave us. However, they did not give us the total moles, so we need to figure that out based off of the masses of all the gases present in the question itself. So, meaning we need to add the moles of CH4 plus the moles of hydrogen gas. In order to do that, we're going to need to calculate the moles of both because they didn't give it to us in moles. What did they give it to us in? They gave it to us in grams, right? They gave us the gram amount of CH4. They gave us the gram amount of H2. But we can use the molecular weights to convert those gram amounts to mole amounts. Once we have them in mole amounts, we add those mole amounts together to get the total moles. So starting with moles of CH4, we take the mass of CH4, 8.5 grams, and divide it by the molecular weight of CH4, which 16.042. So dividing those amounts, we get the moles of CH4 to be 0.52986. Next, we do the same thing with hydrogen. Now notice this one I wrote out a little bit quicker or in shorthand. So 8.5 grams of hydrogen gas divided by the molecular weight of hydrogen gives us the mole amount of hydrogen. So now we have moles of hydrogen and the moles of CH4 gas. We add those two amounts together to get our total moles. So 0.52986 plus 4.21627, we have a total mole amount of 4.746. So this is just our NT that we are using in the denominator of this equation. All right, so now let's put it all together. Now that we have our total moles and then our partial moles of CH4 and H2 gas. So remember, we're using this equation here, Na over Nt equals Pa over Pt. We're going to use it twice. One with moles of CH4 and the other time with moles of H2. So our total pressure, I'm going to add to our list of knowns. That's the 1.32 that they gave us in the question itself. So to solve for the partial pressure of the CH4, we're going to use this equation here. We need to rearrange that equation to solve for partial pressure. So we want this P sub CH4 by its lonesome. So we need to move the total pressure to the other side of the equal sign. We do that by multiplying both sides by PT. When we do that, the equation becomes total pressure times the moles of CH4 divided by the total molar amount. So plugging in the values for CH4, so total pressure is 1.32. The partial mole amount for just CH4 is 0.52986. We're dividing that by the total mole amount, which we calculated to be 4.746. After calculating it out, we get an answer of 0.15 atm. So that means out of that 1.32 atm of total pressure, 0.15 of that is due to the CH4. The rest of it is going to be due to the H2. So at this point, you can either do a subtraction to figure out the partial pressure of H2, or you can redo the same calculation we just did using the hydrogen gas amounts. So I'm going to do it the long way so you can see the problem done more than once. So for the partial pressure of H2, we're using the same equation we did before. It's just this time we're using the mole value of H2 and the partial pressure to solve for the partial pressure, of H2. So we rearrange the equation once again to get partial pressure by itself. So here we have the partial pressure of H2 all by itself on one side of the equation. So we take total pressure times the molar amount or partial mole amount of H2 divided by the total moles. So plugging in our knowns, we get a value of 1.17. So you'll notice if you take, I'm going to highlight this in green now, the 0.15 pressure from the CH4 and you add that to the 1.17 partial pressure from the hydrogen gas, it is going to equal the total pressure, 1.32. So kind of a nice little check you can do to check your work. Now let's take a break from some calculations and talk a little bit about theory. So we're going to look at kinetic molecular theory. So what do you need to know about the kinetic molecular theory? Well, first off, the volume of the space needs to be greater than the space occupied by the molecule. Obviously, a molecule couldn't fit in a space if the volume of the space wasn't bigger than it, or at least as big as it. So that's kind of a common sense when you think of it that way. Now, number 2 here, the molecules are in continuous, random, and rapid motion. So they're gas molecules, right? They're always moving. They're flowing. They have a flow to them. It's random and it's quick. The average kinetic energy of molecules is affected by temperature. So we just said molecules are continuously moving and it's random and it's fast. Well, number 3 is saying, and that speed, that energy is going to be affected by temperature. Because, as we know, if we heat something up, molecules are going to move faster. If we cool something down, molecules are then going to move slower. So the kinetic energy is affected by how fast the molecules move, because by definition, kinetic energy is moving energy. Number 4, perfect elasticity. Okay, so this is not something we see in the natural world. So there's no loss of energy after the molecules collide. So when 2 molecules hit each other, they bounce off each other and continue moving in opposite directions at the same speed with the same amount of energy. Last but not least, the average kinetic energy of a gas increases with an increase in temp. So we kind of stated that already in number 3. We just didn't say how the kinetic energy was affected by temperature. So number 5 is just stating that it's affected by temperature because an increase in temp will increase the kinetic energy, just like a decrease in the temperature will decrease the kinetic energy of a gas. So essentially they're proportional. Let's use the kinetic energy theory and apply that to the kinetic energy of gases. So if we wanted to figure out the velocity of a gas, and velocity is directly related to kinetic energy, we would use the equation below. Notice the equation below, along with having the gas constant R and temperature in it, it also has molecular weight. So to use this equation, what it's saying is that molecules, they have various speeds being velocities, and those velocities are dependent upon their molecular weight. So we can predict if we're comparing 2 or even 3 different gas molecules, which one will have the higher velocity just based off of its molecular weight. That's what that's saying. So we don't even necessarily need to use this equation as long as we're trying to figure out a comparison rather than exact velocities. So if I'm predicting the average velocities for all of the gases given here, they are going in order of decreasing velocity, meaning the fastest gas, or the gas with the highest velocity, is going to be hydrogen gas in this case. Next fastest would be helium, going all the way down till we get to the slowest of this group, which is krypton. Now notice, let's look at their molecular weights now and how that applies to velocity. Now the molecular weights are going in order of increasing molecular weight. So that tells us that velocity and molecular weight are inversely proportional, meaning that as the molecular weight goes up, as the molecular weight is increasing, the velocity is decreasing. So we have krypton here, which has an approximate molecular weight of 84 grams per mole. Now krypton is the slowest out of these gas molecules because it has the highest molecular weight. It's the heaviest, so it can't move around quite as quickly. Now hydrogen gas is going to be the fastest, the highest velocity. Why? Because it has the lowest molecular weight. It's light. It can move around a lot easier. And that's what this chart off to the right is showing. So you can see hydrogen gas here, velocity versus its molecular weight, all the way up at krypton gas. Much lower velocity, right? Under the 500 mark for krypton. Now keep in mind that these molecular weights that I have written here, they are approximate. Okay, so these are not exact with the decimal points. I just wanted to give an overview of how molecular weight and velocity are related. I do also want to note that this is assuming the temperature is the same for all of the molecules being compared, right? Because if we increase the temperature for just one of the molecules, that's going to make the molecule move faster, its velocity go up. So we're assuming constant temperature and pressure in this comparison. So the last law we're going to look at is going to be Graham's law. We're going to use to calculate from, and in order to calculate using Graham's law, we first need to discuss the difference between diffusion and effusion. So you can see we have pictures of both examples below. So diffusion is going to be this first one. Now diffusion refers to the gradual mixing of gas molecules throughout a container. So this mixing occurs spreading from a high area of concentration to a low area of concentration. Okay, so they're free to move wherever they want until they are thoroughly combined, mixing the gases. Now effusion then specifically describes the escape of gas molecules from a container through a tiny opening in a vacuum. So here there's a barrier, notice, with a tiny opening. So the movement of the gas molecules move throughout that small opening until the mixture is complete. So Graham's law is using effusion in its calculations. So it calculates effusion rates. Now what Graham's law states is that lighter gases move faster and effuse more quickly than heavier gases. And if you think about it, that makes sense. We actually saw that when we were comparing velocity and molecular weight, right? Hydrogen gas, which was a lighter gas, had a much higher velocity. It could move faster. And since it could move faster, that makes sense. It would effuse more quickly than the slower, heavier gases. And that's all they're showing here. So helium, for instance, has a very low molecular weight of around 4 grams per mole. Now, if you put that in an effusion chamber, look at all the molecules that effused. Quite a few of them. Right, now let's use a much larger, heavier gas, in this case ethylene oxide. So look at that guy. That guy's got to be, I don't know, around 40, maybe even higher grams per mole, so much heavier gas. And now if you look at its rate of effusion, only a few molecules effused through that vacuum tiny hole. That's due to the heavier side. So using this through experimentation, Graham's law came up with the equation shown here. So the equation states that the rate of the light, so rate of the lighter gas divided by the rate of the heavy gas is going to equal the square root of the molecular weight of the heavy divided by the molecular weight of the light. One thing I want you to notice on this equation is that the rate has the light gas in the numerator and the heavy gas in the denominator. Now when you go to the other side of the equation with molecular weights, notice the heavy molecular weight is in the numerator now and the light molecular weight is in the denominator. I just want you to notice it switches because a lot of times your eyes don't see that when you're using the equation and you assume that light needs to be in the numerator on both sides. It is not, so just be aware of that. So faster gas is the lighter one, slower gas is going to be the heavier one. So that's the takeaway here. So next what we're going to do is we're going to look at how to use that equation. So an example of when you need to use Graham's law equation. So for Graham's law practice, this is the type of question that you would expect to see. So we have carbon dioxide and they give us the molecular weight. Effuses through a pinhole at a rate of 0.363 milliliters per minute. Now this is the rate that is going to go on one side of the equation. Notice the units on it. Now the units on the rates don't necessarily matter. What matter is that the units on the rates need to be the same. So what do I mean by that? Well, if we keep reading, it continues to talk about another gas. It says another gas effuses at a rate of 0.232 milliliters per minute. So what I mean by that is as long as these rates are both the same units, in this case milliliter per minute, then you just leave them in those units because they're going to cancel each other out anyway. So they're both in the same unit, so we don't need to adjust. Now, continuing to read, the question asks, how much slower is the unknown gas compared to carbon dioxide? So notice they're saying how much slower is the unknown gas. So they're telling us that carbon dioxide is the fast one. So if carbon dioxide is the faster of the two, that means that it is going to be the lighter one, the less heavy one, essentially. It's then asking us to solve for the molar mass of the unknown gas. So let's write down our knowns and unknowns. So we have the rate of carbon dioxide. Notice it's faster of the two. The rate of the unknown going a little bit slower, and then the molecular weight of carbon dioxide. So we are going to use Graham's law equation. We're going to plug in our knowns and solve for the unknown. So which one is faster? Well, just looking at those rates, you can see that carbon dioxide is going to be the faster one because it has a faster rate. Since it's faster, we can conclude it's also going to be the lighter one, the one with the lower molecular weight. This is important because we need to know where to plug in the appropriate materials. So to figure out the ratio of unknown, so like how much slower is the question we're answering now? How much slower is the unknown gas compared to carbon dioxide? We take So putting Graham's law into practice, we're looking at carbon dioxide gas. They gave us the molecular weight of it. E fuses through a pinhole at a rate of 0.363 milliliters per minute. So that is the rate at which carbon dioxide is moving. Now notice the units on this. So for the rate, the important thing about units is that the units are the same between the two gases that you are comparing. What do I mean by that? Well, if we keep reading, first off it says the temperature is at 25 degrees Celsius, and then we get to another gas effuses, and notice its rate, 0.232 units milliliters per minute. So as long as they're both in the same units, there's nothing you need to change with them. Okay, can be meters per second, miles per hour, milliliters per minute, as long as the units are the same between the two gases you're comparing. Now, next it's asking what is the molar mass of the unknown gas? Well, first off, we already know quite a bit of information here. Notice they're asking how much slower the unknown gas is to carbon dioxide. So you can see just by looking at the rates that carbon dioxide is the faster of the two because it has a rate of 0.363 and the other gas is slower at 0.232. So let's look at what we know. Carbon dioxide, 0.363. The unknown, 0.232 milliliters per minute. So carbon dioxide is clearly the faster of the two. So we've already determined which one's faster. Next, we need to determine the molar mass of the unknown using Graham's equation here. So we've established which one's faster. Now it's important to note that the faster one is always the lighter one as well. So we will expect the unknown, once we solve for the molar mass of the unknown, for it to be heavier than carbon dioxide, meaning its molecular weight should be higher than this 44.01 grams per mole. That's a nice check we can do at the end, making sure that the mass is indeed larger since the unknown is the slower of the two. So to figure out molar mass of the unknown, we're going to have to rearrange the Graham's law equation. So we rearrange it, getting the molecular weight of the heavy one all by itself. So notice to do that, we needed to get rid of this square root. So we get rid of the square root by squaring both sides of the equal sign. So if I square this side, that gets rid of the square root. And then if I square the other side of the equal sign, that's how we get this squared around the rates. So once the equation is rearranged, we can then plug in our knowns. So to plug in the knowns, notice we are taking the molecular weight of the light, and we established that the light one was indeed carbon dioxide, so that's why we use the molecular weight of carbon dioxide here. Then we take the rate of the light one, once again, the light one being carbon dioxide, 0.363 milliliters per minute, divided by the rate of the heavy one, which is the unknown, 0.232. We make sure once we divide that we square that value and then multiply it by the molecular weight of carbon dioxide, that 44.009. We then get a molecular weight for our unknown at 108 grams per mole. Doing a check, it is indeed the heavier of the two, so it makes sense that it is the slower one.